Thank you so much. Thanks for having me here speaking, and thanks to Rupak Biswas for bringing me into this forum. It's been quite an educational experience for me learning about HPC, feeling a bit guilty that I didn't know more already beforehand, but good to get the fire hose. As I said, I lead the data sciences group, so I come into this from a machine learning, data mining perspective. That's true for much of my group here. We're about half PhDs, half non-PhDs, and some people like me come into this from a machine learning or data mining background, but we have, as an example, 2 PhDs who they got their degrees in mechanical engineering, but found ways to bring machine learning into their work and decided to move forward in machine learning, and they fortunately came to us. And our funding sources are mostly NASA. So there are sources like aeronautics and space exploration where funding tends to be more directed, where they've already said, okay, here's the need for some machine learning, data mining, here's some funding, go do it. Then other areas like within science, whether earth science or space science, they're driven by competitive proposals. So it's any combination of NASA and non-NASA people proposing to a NASA program to do work. NASA people are not given any sort of advantage. And then in some cases, we also get non-NASA funding. So it's quite a mix of different ways we end up working. And at the top there, that just shows what we would be able to put on a T-shirt if we could have some made, which is really the data mining R&D for application to NASA problems. There is also a sister group actually at NASA Langley that it's a little less research oriented, a little more on the development side, making use of tools that are already there and doing things on a shorter turnaround, whereas we certainly start by using what's available, but then we tend to get into problems where it's known that the existing tools are not going to be adequate, so some research is going to be needed, and it's already decided that more time is going to be devoted to our work. So we've seen better versions of this than what I've been able to put up here. But so I won't go into huge depth with this, but really what I'll say is that, so I mentioned that we're the data sciences group, and we really cover this full range of, so of course machine learning, neural nets, you have to say something about deep learning these days. And then there's of course data mining, which is taking machine learning and also bringing in databases, and there the idea is how to leverage massive amounts of data. And then the big data is really meant also to deal more with the infrastructure, things on the storage side, and so we really use data sciences to cover that full range, which is the area where our group works. And then certainly there are other areas within NASA, even within the division, that look at things like other areas of artificial intelligence, like planning and scheduling, robotics, and the like. As far as collaborators, we certainly we work a fair amount with universities. Of course, we have provided, in some cases it's our own funding, and in some cases it's funding from other organizations like NSF, doing basic research in data sciences and research in some of the other domains. Then we work with them to develop things further for NASA problems. Certainly we work a lot with industry. We have various data sources, like for example within aeronautics we have partner airlines who have agreed to share their data with us, where we develop algorithms, test on their data, and in exchange for that they of course find out, they get insights from us. And then at NASA, our role, we really sit in between the universities and industry, applying the basic research, seeing how far we can get with that, but then making developments for NASA needs, as I described. We have a fair amount of domain expertise as well in, of course, in aeronautics, space exploration, earth science, and space science. And NASA has some of its funding programs, so sometimes we actually will fund a university and then we'll collaborate with them, or we will fund industry through NASA research announcements or NRAs or the SBIR programs, and we'll work closely with them then to advance work for NASA's needs. And then we do every now and then also work with other government entities for the full range of things, data sources, domain expertise, and in some cases funding, whether it's direct or in many cases it's indirect ways that I've described, like universities getting funded by, say, an organization like NSF, but using one of our target data sets, say. Now, I just put this up just to kind of show, this is really meant to say, why are we fussing with data science and machine learning? It's just because there's, I think, we kind of assume what is shown here, which is that there's some kind of system of interest that is operating in some sort of environment, and we throw some sensors on there, and we end up getting some data that is the result of the operation of this system. And essentially, we want to reverse engineer that system and the environment to try and understand what is really going on with the system behaving in its environment. Certainly in many cases we have models that give us a pretty good idea of what's going on in most cases, but oftentimes it's known that there are holes in those models, especially in unusual or anomalous cases. So the thought is that if we can learn from the massive amount of data that is generated, maybe we can learn something beyond what is in the models. So this is just a high-level example of the range of NASA machine learning problems. So I show within aeronautics, for example, there's anomaly detection. So of course, carriers are already looking for various problems, but it's known that there are problems that they don't already know about, so we'd like to find them. Precursor identification, this is looking for precursors to known issues. What are the factors that may have contributed to those anomalous issues taking place. Text mining, so there are aviation safety reports, trying to look for patterns within those. Within Earth Science, there's of course anomaly detection. There's the problem of filling in missing measurements. I'll talk a little bit about that later. Then there's teleconnections. So this is relationships between climate and weather phenomena in different areas of the Earth. Probably the most well-known one is El Nino, where you have increased rainfall in Australia known to relate to drought conditions on the west coast of the United States. But there are many other teleconnections that are known, and it is thought that there are many more that are still unknown. So there's the desire to find those using machine learning and data mining techniques. And then generally climate understanding. So there's a project I won't end up talking about where we got funding to use symbolic regression trained on data to learn how vegetation is impacted by various climate variables. So that goes, of course, to climate understanding. Then within space science, we've been doing some work to take data from the Kepler mission for identification of planet candidates and trying to automate that process using machine learning methods. And then within space exploration, there's of course quite a number of complex engineering systems that go into space exploration, and systems health management is very important there, so we've been doing some work there. And we're also doing a bit of work on astronaut health. So in this case, this is looking at images of the retina and trying to identify the vascular structure there, because given one tomographic image, apparently it takes scientists anywhere from 10 to 25 hours per image to actually identify which are the arteries and the veins and properly colorize that. The thought is we can use machine learning methods to make that substantially faster. And it turns out the phenomena that show up in diabetic retinopathy with changes in the vascular structure are apparently phenomena that also happen in astronauts. So that's where NASA's interest comes into this. So this is the example of filling in missing measurements within Earth Science. So here, the idea is that there's a satellite called MODIS that came online in 1999. And there's a particular channel within that, MODIS channel 6, that is thought to be particularly good for detecting clouds over snow and ice-covered regions. Now, as you can imagine, that's kind of a difficult problem because everything there is white. But this channel 6 is thought to be good for that. But now, that channel does not exist for the older instrument AVHRR that came online earlier in 1981. So we thought, okay, here's a simple thing you could do. There are 5 channels within MODIS that happen to loosely match up in terms of the wavelength bands with the 5 channels that are there in AVHRR. So why not use machine learning to train a model to predict MODIS channel 6 as a function of the 5 common channels that you see in MODIS, and use that to essentially generate for AVHRR what AVHRR channel 6 would look like. When my then boss suggested it, my first instinct was, oh, this seems kind of stupid. I had just come out of doing a Ph.D. 2 years earlier, created a cool new algorithm, and I thought, you gotta need some more sophisticated algorithm here. You know, you can't just do something simple like this. But it actually worked surprisingly well. We use this over Greenland. As you can imagine, it worked better in the summertime when you had more visible light there. In the spring and the fall, was kind of iffy, and then of course in the winter when you had darkness pretty much, it didn't work very well. But turned out to be pretty cool. Then that's a problem where I showed how it's the accuracy of the result that's pretty important, but of course with earth science you end up quickly dealing with ludicrous amounts of data, and so that's why we have some research that's really focused on efficiency. So in this case we developed, did develop an algorithm for anomaly detection on massive earth science data sets. So in this case, it's a distributed, what is called a one-class support vector machine. That's a known algorithm for anomaly detection, but we developed a distributed version of that where we were able to show that we get about 99% of the accuracy of what you would get if you were able to centralize all of the data. But we only get about a 1% communication overhead added beyond what you would get if you had an embarrassingly parallel algorithm running. So from earth science, just moving to aeronautics. So this depicts the kind of problem that we're looking for here. So we assume that, say, this may be, let's say, a commercial aircraft, or you may have a group of commercial aircraft taking off and landing at a given airport. And overwhelmingly, the system operates in a safe mode. But there may be a certain context within which, with relatively low probability, but still higher than what you would prefer, you end up in what you can call a compromised state. Now, most of the time, again, the system does recover, but once in a while then you get into something what you might call a more anomalous state. And then, again, most of the time things recover, but sometimes you end up in what's called an incident or an accident. So we really want to find this full sequence of, what are the conditions where by themselves they're safe, but you're more likely to have some kind of an incident leading possibly all the way to an incident taking place. Now, the industry already has an approach, what is referred to as exceedance-based methods, which are essentially rules. So they come up with things like this. So during landing, when the altitude is 1,000 feet, if the speed is greater than 250 knots, that's what's called a high-speed exceedance. So for that particular flight, essentially they check a box and say, okay, that exceedance was violated. There are other exceedances as well. And if a particular flight has more than the normal number of exceedances, and if the flight crew has not filed a safety report, then safety analysts will go and ask them what happened. Now, pretty much by definition, this kind of method is great for looking for the problems that you are looking for, but it's not going to necessarily find anything new. So that's why it was about 10 years ago that we figured we can go into this with data-driven methods like machine learning, where we really let the data speak for themselves. We can use these methods to eliminate the vast majority of statistically normal data, where we are assuming that statistically normal data are all operationally normal just because the system is an overwhelmingly safe one. So we figure this is a safe assumption. Now, among the data that are statistically anomalous, fortunately, by the way, this is not to scale, among the statistically anomalous data, certainly you're going to get some that are known problems, maybe the exceedances that you mentioned earlier, and then there are going to be some that are false alarms. But we've found enough unknown problems that our partners have never told us to just go away. And we've had pretty good results in running these data-driven methods, yes, having some false alarms, but identifying some good insights and having, for example, a partner airline actually modify their daily exceedance detection method. So this is just an example of the kind of problem we have found. None of you who are flying back really should worry here. But this is an example here where we trained on, in this case, data on a per runway per month basis, just so that we're doing apples to apples comparisons. And the algorithm was able to figure out that this is kind of the typical range, these lines that are shown in gray, the typical range of approaches that you get to this particular runway. Now, this trajectory that's in red showed up as anomalous because of its somewhat unusual shape. You can see here that it was coming in for approach. It overshot the runway, was unable to line up in time to land, so then it had to do a go-around. And you may be able to see that it just barely overshot the runway a second time, actually, but this time was able to stabilize itself and land properly. So in this case, it showed up as unusual just because of that trajectory shape. And we've done some of this kind of thing also with onboard flight recorded data, where we found things like unusual sequences of autopilots or increases in altitude, decreases in airspeed during takeoff and other such things. We also, in addition, we developed an anomaly detection algorithm based on the one-class support vector machine, again, that is able to take the different types of data, like the discretes, which are like the autopilot modes, and then continuous variables as well. And we're able to find this anomaly. We also developed a precursor identification algorithm that was able to take things like this go-around and was able to automatically describe, to identify precursors that were not necessarily contiguous in time. For example, with go-arounds, we identified some cases of potential overtake of one aircraft, potentially overtaking the one in front of it, or going too fast, and therefore probably being directed to do a go-around. So that's really kind of the algorithm and the problem perspective, but then when you really want to make it work, you end up these days with the problem of what we all know as the 4 V's of big data. Big data was a term actually devised by 2 scientists at NASA Ames in our supercomputing division, actually, where they were referring to the problem of volume of data going beyond what you could have in a particular, in a single computer. And so certainly we have that problem. This is just showing the case of aeronautics, but of course in earth science and other areas we run into some of that as well. But there are also other problems these days. So we've already talked to some extent about the velocity of data. New data is constantly coming in, so you have to learn from that. Veracity is an issue. We've had problems of like flight tracks stopping and starting in midair, other violations of the laws of physics. And then you also have a variety of data. Like I already described the discrete and the continuous data, but as much as possible we'd like to bring weather data into it. I described the aviation safety reports. We'd like to bring those as well. And in spite of all of that, we would like to be able to really solve all of the problems that I described before. So this is, now I'm going still lower level, so I've described, okay, the issues with the data, but we have to run all of this stuff on some sort of a platform, and this is describing the NASA Earth Exchange, which was developed for Earth Science, and what this shows is that we have the supercomputing. This is the NASA Pleiades system. We also have very large data sets, model data, satellite data, and then we also have these various user communities. So the idea here is to facilitate things like project sharing, like sharing of results, data sets, and the like. And so this is really the hardware, but this shows also what the software infrastructure at a high level. So we have in some cases users that really want to run directly across the storage and the compute. So they have their own scripts that they're running, but some of them would rather work at a higher level. So we have a project that was funded before that allows you to set up workflows and share analysis steps under this infrastructure. So the community the community infrastructure that I showed before, here where you can have various user communities, the code base for that is one that we developed that is also being used within systems health management for aeronautics in this site called DashLink. So I've given the URL here. Any of you can become members. I'd be happy to approve your membership in this. And the idea is that just like with the NASA Earth Exchange communities, we are setting up communities around data mining and systems health management, facilitating sharing of data sets. We open source all of the algorithms we develop and make them available here. You can set up project pages, make publications available and the like. This is just showing last week we ran a machine learning workshop at NASA Ames. Reed's colleague Tim Randall spoke about Charlie Cloud there. We had Natalia Vasilyeva speak there as well. And we had several in industry, academia, quite a few NASA people, really to lay out the space of how we saw different groups contributing to machine learning for NASA problems. What NASA's role is, industry, and academia, kind of as I described earlier. And we had breakout sessions as part of this as well to lay out plans for the future. And we will be putting together some sort of plans for the future for different kinds of programs and projects out into the future based on the results produced by the breakout sessions at this workshop. So Michael already gave a very good description of this, including NASA's involvement in the Preparing for the Future of Artificial Intelligence, where Rupak was a representative, and then the AI R&D strategic plan where I was involved. And certainly that engagement is going to continue in the future in the form of various projects. So this is just kind of summarizing some work. So far we've really been doing data mining and machine learning at the desktop. So this is a scientist or domain expert working at his desk, supplying data, getting some kind of result, and then we're not necessarily involved with what he does in the future. We really want to go from that to more in-time, real-time online monitoring, even learning to improve the analytics process. So I described the workflows for Earth science. Maybe can we learn on those workflows to help actually improve the analytic steps that scientists go through. Certainly in the future, we want to go from producing research code, which we do, to more usability, to improve usability for portability for analytics deployments, have machine learning be part of a process with embedded systems and autonomous systems, and using a variety of different platforms. We described use of HPC, GPUs, conventional CPUs, quantum, all in the best way possible and really on the fly. That's about what I'd planned to say. Please feel free to ping me in the future with questions or now.